Hello, everyone. My name is Mark Toomey. I am a Senior Solutions Architect for Amazon S3. I'm here with my colleagues today, Bijeta Chakraborty and Frank O'Young from March Networks, and we are going to talk to you about Amazon S3 vectors. Now, thank you for joining us at reInvent. I don't know about you, but my fitness tracker thinks I'm running for my life when it comes between sessions with all the steps that are going in. But what we're going to discuss here today is a problem that we have solved and a problem we have created. The problem we have solved is we have created the Star Trek computer. Yes, we now have something where you can ask it a question, it understands what you means, it'll hallucinate an answer and then try and kill you in the holodeck, like every episode of Star Trek. But no, we now have artificial intelligence systems that understand meaning. They understand meaning for the simple reason that when we look at things like the text, images, stuff like that, computers have no idea of this. They don't know how to analyze or synthesize these things. And what we have is we have vectors. Vectors are how we encode meaning into mathematics. What are vectors? They are ordered array of numbers. They're ordered array of numbers that allow us to encode meaning into mathematics. Text, images, sounds, movies, they allow artificial intelligence systems to analyze and synthesize. Your brain does this automatically. Evolution has built it that way. You're doing it all the time. You're doing it right now. Computers are mathematical engines. So we need to we need some form of intermediate layer for a computer to understand meaning. That intermediate layer is what we call a vector embedding. You want to bear with me because we're level setting just for this bit. Then we're going to get into S3 vectors. What are vector embeddings? They are the universal language of meaning in computer science. If it doesn't have a vector embedding right now, it'll have one soon. It is how we are turning the world. We are allowing artificial intelligence systems to understand the world, understand us. We have to use some form of mathematics to do that. A vector embedding is the equivalent of a brain scan of an embedding model. You have these incredibly powerful embedding models available from Amazon through Titan or it's Nova and all these other models, third-party models that are available out there, things that are available in Bedrock. You pass it something. It could be a sentence, it could be a paragraph, it could be a document, whatever's going on, media, image, whole bunch of pixels. And what the embedding model thinks about that is what becomes a vector embedding. And of course, these things are very tightly aligned then as a result of it because you are capturing a layer inside an embedding model, converting that into a large amount of mathematics, which then you probably want to store somewhere. It is like the long-term memory of artificial intelligence. That's what vectors are. Now, if you look at the graphics here, and I try and use a laser pointer, I'll probably turn all the lights out, it'll go to heck. But if you look at some of the embeddings we have here, this is actually music, different music tracks that we have. You'll notice that they're similar colors, they cluster together. And that's what vector embeddings do when they understand stuff. They cluster together. What makes vector embeddings special? I mentioned already, converts data into an ordered array of numbers. The features of something, what an embedding model thinks about what you have shown it, gets encoded across all of these numbers. The individual numbers we call dimensions, usually 32-bit floating point numbers. And you end up with this vector embedding, this one string that could go on for tens of pages, and that entire thing is evaluated all at once. So vector embeddings, quickly, they start stacking up. That is the problem that we have created. We have created a cost and complexity problem. We have given artificial intelligence this long-term memory, but now we have created a cost and complexity model because these things need to be stored. They need to be managed. They need to be available. That's the problem that we look to address with Amazon S3 vectors, and Bijeta will get into that in the future, in the near future. Now, because vector embeddings are mathematical, you can perform arithmetic in them. If you were to present the idea of $1 I don't have one on me right now because everyone's tap right now. I mean, but everyone is like a card or some form of tap. But if you were to present a dollar, it is a unit of exchange. It is a monetary instrument. It's legal tender. There's a physical object or not, right? Because it can be a virtual object through some form of code. What an embedding does is that actually converts all of that into a string of numbers. If you were to take the meaning of a dollar and subtract the meaning of the United States from it, but add the meaning of Europe, and then ask, what is this number to the embedding model, you're going to get back a set of results. In this case, the most similar result would be a euro. This isn't a party trick. It's how vector embeddings work. You can do this with other ideas. It's a principle of computer science. You can add, subtract, multiply these numbers, and get answers from them. How do we generate embeddings? Well, S3 is the world's greatest repository of unstructured data. I would say, outside of the great library of Alexandria, it is in history, I'm going to claim that. Can you imagine claiming history, getting on stage and saying, in history, Amazon S3 is the greatest source of unstructured information. But I'm going to do it, and it's recorded, so I can't back out now. So it is for unstructured data, it is the cloud scale unstructured repository, the largest one in the world, I would argue. Well, you can use that as a data source, and then you need to chunk that up. You're not going to provide everything. You decide you're going to take all this data, could be massive movies, could be text, could be images, whatever else is going on, the scanned images of the world's art, and then you present that to an embedding model. We support, inside AWS, we have many third-party partners as well as our own models. The embedding model then generate those brain scans, but they need to be stored somewhere, and that goes into usually some form of vector store. Amazon offers several vector stores. We're talking about Amazon S3 vectors right now. How do you get the meaning back out once you've stored it? How do you like? It's like I've done all this. I've taken the brain scans. I know what the model is thinking about or what it is perceiving at the time. How do I do that? Well, you'll need to search across all of these vectors, and this is a mathematical operation. Traditional databases are absolutely useless for this work. We are in the world of meaning. We are in the world of similarity. We are in the world of mathematical distance. So traditional databases don't work in this case. A traditional database, rows, tables, columns, joins, you can do joins and all these things. It's no good. You need specialized algorithms. This is about distance. And to work with distance and to do this effectively and to get an answer back at a reasonable amount of time, you need to narrow the search space, measure distances between all these different points of mathematics that you've stored, and then rank and return a set of results. We have the idea of a nearest neighbor search. Vectors are in the domain of similarity, finding things that are similar, not exact. If you want exact matching lexical searches, that's what traditional databases are for. In my house, let's say recommendation engines, you see them for things like Prime Video or any other streaming service. These are the backbone of the internet and your experience with the internet right now, something that will recommend you something perhaps that you like. I watch maybe a show like a superhero satire show, like The Boys, Amazon show. Maybe I want something more like that. Maybe I want other shows like that. How would I find those? Recommend these things for me. Since my account tends to be the default one, other people watch things in my account, things that maybe I would not be interested in, which means I somehow get weird results. Like, for example, I could watch historical epics or superhero satires, and I will get recommendations for The Summer I Turned Pretty. This is a show aimed at young women and teenage girls. There's also various Korean dramas, because there's a lot of that watched in my house as well. And no matter how many times you tell someone use your own account, no, recommendations are always interesting. I mentioned earlier that clusters, that vector embeddings cluster together. Well, if you were to turn a television show into a vector, that also will cluster together. And that's how a system can recommend something to me. Let's say we narrow the sphere here. We have narrowed our search area. I'm just interested in superhero satires. This index has other things in there too. There could be production teams who have worked in different shows. There could be actors that are common amongst all these different shows. But we have narrowed the search space, gotten in as close as we can, as quickly as we can, using specialized algorithms to do that. And then we're going to calculate distances between everything in here to rank and rate what is interesting to me. Once we rank these things and we return results, I've done a vector search for whatever the boys is. It has brought back, having recommended a superhero show to me, other shows like Invincible, another Amazon show. How amazing, at an Amazon event, and I'm plugging all the Amazon shows. But there are other shows here that are not Amazon shows. They recommend those too. And it also recommends The Summer I Turned Pretty no matter what I do to try and prevent it from doing that. All of this, turning everything we have into recommendations, into meaning, has led to this explosion of vectors. With these embedding models, they tend to be specialized. Some do text, some do audio, some do video. But giving people the ability to search across all of these medias, you could create billions and billions. As Carl Sagan used to say about the stars in the galaxy, billions and billions of things out there. I can't do his accent. But you create these billions of vectors. All of this adds up. A vector embedding can be 4K. Then you could be done with your embeddings because you're deciding that maybe I have movies. Maybe I need scenes from movies. Well, depending on how many movies you have, you can be approaching gigs, tens of gigs for just that one data set. Granularity matters here. The more you decide, the more granular you want to get with something, the more vector embeddings you're going to generate, the more storage you're going to use. The mathematics compounds fast. Vector storage can reach gigabytes, terabytes, and there's always someone out there who's going to do a petabyte. One of you out there, I'm going to do this whole thing where I said no one's ever going to hit that number, and someone's going to say I'm going to hit that number, right? But the vector explosion is out there. We have more stuff coming all the time, and as this artificial intelligence proliferates, you're just going to have more of these, not less. There will be more vector embeddings for you to manage, not less, going forward. For that, you need a specialized vector store. I mentioned that you can have pages of numbers. We call that dimensionality. The more collections of numbers you have, the more dimensions you have. What are dimensions? Dimensions are features of something. Everything gets encoded into one string of numbers. So you need something that can handle pages and pages and pages of numbers for one embedding. It needs to be able to do that search where you can zoom in very quickly, calculate distances between everything that might be interesting to you, and return results in milliseconds, under a second. You need to be able to do that fast. It also needs massive scalability. You need massive scale in this stuff. And specialized indexing algorithms to make sure that the data you put in is there and available immediately. Storing vectors at scale gets expensive fast. There are compute costs, baseline compute. You're not doing any queries, but you're still burning CPU cycles, and you're paying for that. There's memory requirements. RAM is about to get very, very scarce in our industry. I've seen today some providers actually pulling out of the consumer market because they're focusing on the enterprise market for RAM production. But memory requirements for vector stores tends to be incredibly large. We're talking tens of gigabytes, hundreds of gigabytes for performance. And then there's licensing costs. Enterprise-style licensing for these vector stores. You're going to pay for backup, you're going to pay for your queries, you're going to pay for anything else that's going on there. You pay. And that's why in July of this year, in preview, we introduced Amazon S3 Vectors, the first cloud object store with native support to store and query vectors. We've taken S3 scale, S3 performance, and made that available for vectors. It's when you consider internet scale, cloud scale, S3 is the thing to think about. We're doing that for vectors. What did we deliver in July? We delivered sub-second vector query performance at scale, less than a second. Up to 90% lower costs for what you're doing, uploading, querying, et cetera, and the ability to store billions of vectors. We had an index size of 50 million when we came out first. That has now changed. And to talk about what has changed and where Amazon S3 Vectors is today, I'd like to invite Bajeta on stage, product manager for Amazon S3 Vectors, who's going to take you through vectors now and vectors going forward. Bajeta, thank you.
Thanks, Mark. Hi, everyone. My name is Bajeta Chakraborty, and I'm really excited to talk to you all about S3 Vectors. Just like Mark said, Amazon S3 Vectors is the first cloud object store to have native support in storing, querying, as well as uploading vectors. At public preview, we were delivering sub-second latency, which is critical for you to build AI applications that need instant query results. We also shipped a specialized set of APIs that are purpose-built for vector workloads, making it really straightforward for you to build search applications or RAG workflows. And for those of you that are building RAG workflows, right at public preview, S3 Vectors integrated with Bedrock knowledge bases, as well as Amazon OpenSearch to build powerful hybrid search applications. Since that public preview date, in the last 4 months, we've had tens of thousands of customers using S3 Vectors. In fact, we've seen more than 250,000 indexes created. They've ingested more than 40 billion vectors on S3 Vectors, and just in the past 2 weeks, we crossed the 1 billion mark of queries that customers have ran on S3 Vectors. Let's look into 2 separate examples of how customers are building on top of S3 Vectors. Here's an example of a biotech firm that's using S3 Vectors to build a semantic search on scientific literature. So in this particular biotech firm, we have a team of PhD scientists as well as entrepreneurs whose job it is to find the next science hypotheses or breakthrough hypotheses and turn them into billion-dollar companies. But here's the challenge. When you're looking for the next discovery, you need to first know what's already been researched. And we're not talking about looking through a few documents or even thousands of documents. We're talking about 30 million research papers, scientific journals, information from PubMed, clinical trials, all of that. Previously, in fact, it used to take them weeks. It used to take their scientists weeks to sort of manually review through these databases and piece together insights that they could then put together for their next project. Here's how they're changing that with Amazon S3 Vectors. As you can see on the left-hand side, they're taking all of their scientific documents. These are all those PDF documents, research papers, scientific journals. They're putting them through into a general-purpose Amazon S3 bucket. They're processing them through machine learning models and then generating embeddings on the other side. Now they're ingesting all of those embeddings into S3 Vectors. And we're talking about hundreds of millions of embeddings in S3 Vectors to represent all of the scientific literature. Now let's say a scientist comes along, they want to do a search like find me novel protein targets for autoimmune diseases. They're not having to do manual keyword searches. They're using S3 Vectors to power a top K nearest neighbor search that returns results within a second and also is doing metadata filtering. What we've done here is we've compressed that week-long process or weeks-long process into a sub-second semantic search. Here's a different one. A lot of us are building agentic applications. We're thinking about agents. I'm sure a lot of you in this room are thinking about or building agents yourself. With agents, you have a new version of the same exact problem. Instead of scientists having to go through millions of documents, it's the agents that now need to go through thousands, hundreds of thousands of tools, in fact. When you're building agents for your organizations, you first need to give your agents access to all the tools in your organizations. So these are APIs, Lambda functions, could be your Slack integration or Salesforce integration, it could be anything, database connections, right? And what we've seen is that when you give your agents access to that many number of tools, the agent can get confused. It can even hallucinate and come up with tool ideas that don't even exist. Here's how Amazon Bedrock Agent Core Gateway is changing that with S3 Vectors. When you build an agentic application or you build an agent with Agent Core takes your tool information for example, the tool name, description, parameters, and converts those into embeddings and stores those into Amazon S3 vectors. So now let's say you're trying to accomplish a task through the agent, like find order information or send customer an email. You're not having to get back those thousands of tools. Rather, S3 vectors is doing a sub-second semantic search and giving you back, or giving agent core back, the 5 or 10 relevant results here. Those are just 2 different examples of how customers are building on S3 vectors. In fact, it's been overwhelming looking at how customers are finding different ways of building on top of S3 vectors. We've seen customers build all sorts of searches on text, on images, on videos. There's obviously RAG workflows that customers are using it for. They're using it for building agent memory. We have life sciences companies also using it to store representations or embeddings of like molecular representations, chemical notifications. And as they've been building with S3 vectors, they've been giving us a lot of feedback. Here on this slide are the top 4 things that we've been hearing from customers since public preview. First of all, they've asked for lower latencies. As customers are building user-facing applications, they're building chatbots, they're building more interactive search experiences or recommendation engines, every millisecond matters. Second, they're asking for bigger size of indexes. As their vector applications are growing, they want the infrastructure underneath to scale with it. Faster ingestion of vectors. A lot of the customers want the flexibility of sending tiny batches of vectors to S3 vectors, but want to do it at a much more higher concurrency to accelerate the ingestion process. And then more AWS regions. They wanted to see S3 vectors closer to their data, closer to their users, and in compliance with their regional requirements. We listened to the customer feedback, and in the past 4 months since public preview, we have continuously improved the product. I'm really proud to announce the general availability release of S3 vectors. We're down to 100 millisecond of warm query latency. We've grown the index to 2 billion vectors per index. You can create 10,000 indexes per vector bucket, so you can store trillions of vectors, in fact. And for those of you that wanted the flexibility of sending smaller batches or a vector at a time to S3 vectors, we've improved the write throughput to 1,000 transactions per second. And we've done all of this while keeping the headline the same, that with S3 vectors, you can save up to 90% costs for storing, uploading, and querying vectors as compared to alternative vector solutions. At GA, we've grown 40x, in fact, since public preview. We went from 50 million vectors per index to 2 billion vectors per index. And you can create 10,000 vector indexes per vector bucket and 10,000 vector bucket per AWS account. So essentially, you're storing not billions, trillions of vectors and not having to worry about costs. And this is directly on S3. We're still at sub-second query latency for cold queries. And this is the thing that makes it really cost-effective for batch workloads or infrequent workloads of queries. However, for warm queries, we're down to as low as 100 milliseconds. This is really good for when you have repeated or similar queried data. S3 vectors also automatically caches this data for several minutes since last access. We've added additional capabilities, for example, index-level encryption, tagging for you to do cost allocation and access control, CloudFormation, as well as private link for those of you that want private connectivity into S3 vectors. And we've added S3 vectors to 9 additional AWS regions, bringing the total up to 14 AWS regions since public preview. All right, let's look at some of the core components that make this all work. First of all, you have vector buckets. Now, think of these as specialized buckets that are purpose-built for vector workloads. So unlike traditional S3 buckets that are purpose-built for objects, these buckets are able to meet the unique requirements of storing, uploading, and querying high-dimensional vector data that Mark was talking about. Second, vector index. This is a new data structure within the vector bucket, and this contains your vectors as well as the metadata associated with those vectors. The vector index is a thing that's maintaining the relationship across these vectors to power that sort of a similarity search. And the metadata that you associate with these vectors could really be anything, right? Document ID, timestamp, release year, genre, anything that you want to use to sort of filter your search on or associate with the vectors. And then third, vector APIs. We've shipped a complete set of dedicated APIs that are purpose-built for vector workloads. These are built ground up, and they make it really straightforward for you to do things like upload vectors, list vectors, query vectors, as well as delete vectors when you need them. Let's specifically talk about what the query vectors looks like. This is the thing that you're going to use to do the similarity search, as well as filter on metadata. Query vectors on S3 vectors doesn't just do a similarity search. It does more than that. It's doing a similarity search while filtering on metadata. Here's on the right-hand side of the slide, you'll be able to see what that query vector API looks like. To start off a search, you're actually providing a few things to S3 vectors. Number one, you're providing the query vector. Number two, you're providing the number of nearest neighbor results that you want back, right? We also call this the top K. You're also providing the vector index that you need to query, as well as optionally the metadata that you want to filter on. Now, S3 vectors is not doing a similarity search and then filtering those results against a metadata. It's doing the metadata filtering while doing the similarity search. So it's more likely that you're going to get the results that you actually want. So similar items that also meet your business logic. By default, with the query vectors API, you get back the vector keys. Optionally, you can also get back the vector embeddings, the cosine distance, like we saw in the Prime Video example, the actual scores, as well as optionally the metadata that's associated with these vectors. I'm going to use this particular example of a movie index to talk to you about the different types of metadata that you're able to associate with vectors. There's really two things. There's the filterable metadata, as well as the non-filterable metadata. Filterable metadata, as you can see in this particular example, is like genre, release year, rating, all the things that you want to filter your search. That's your search filter. You're using it to narrow down your results. Excuse me. There's a bunch of operators that we provide to use with your filterable metadata. For example, we have equality, Boolean conditions, as well as lists. Non-filterable metadata is interesting, right? This is something that you're not filtering against. However, maybe you want this data back along with the vector keys as part of your nearest neighbor results. This can contain things like original text, the source URL. The source URL, in fact, can be used to point back to the asset that's being described by this particular vector embedding. Now, the number of key value pairs or metadata in total that you can associate with each vector is 50. So that's 10 times what we had at public preview. By default, all of those key value pairs or all of that metadata is filterable. However, you can specify 10 of those key value pairs to be non-filterable. So how does this nearest neighbor search work on S3 vectors? When you're ingesting vectors into a vector index, S3 vector is organizing your vector space using advanced partitioning techniques to power those semantic searches. So instead of brute forcing searching across millions and billions or trillions of embeddings, in fact, S3 vector is dividing that vector space into hierarchical clusters of vectors. And then when the query vector comes in, S3 vectors is navigating those clusters, pruning away the irrelevant clusters, and zooming into the most promising candidates. As a result of this, you're doing that cosine distance math, the distance computation, only across a subset of your vectors, maybe a few thousands. You're not having to do that across millions and billions of vector embeddings. And the outcome of that is that you're very easily able to similarity search across billions or trillions of vectors in that sub-second query latency for cold queries and as low as 100 millisecond for warm queries. And you're able to do all of this with a really high recall accuracy. This is the last thing that I want to touch on in terms of the internals of S3 vectors. S3 vector shares a lot of the characteristics of Amazon S3 that have made S3 the foundation for millions of applications for nearly 2 decades. First of all, availability. Your vector data has the same 4 nines of availability as S3. Durability, yes, we are 11 nines durable. So your vector data has the same amount of redundancy and protection as any other object in S3. Performance, S3 vectors intelligently caches those similar or repeated query data to get you down to that 100 millisecond of warm query latency. And it also persists that cache data for several minutes since last access. This is similar to how S3, Amazon S3, optimizes reads based on access patterns. And elasticity, finally. S3, as you all know, adapts to your request patterns transparently. S3 vectors does that as well. Just when your vector applications scale from, let's say, 10,000 vectors to millions or billion scale, the infrastructure underneath adapts with it. What we love about this architecture is really the simplicity. You're not having to manage infrastructure. You're not worrying about scaling up your applications. You're not managing complex cluster configurations. This is all S3, right? It's the same scalable, reliable, cost-effective storage that we all love and trust, just purpose-built for vector workloads. So we talked about some of the internals of how all of this works together. Now let's see what it takes to build a similarity search on top or with S3 vectors. So the first thing you're going to do is you're going to start with your source data. And this could be anything, yeah, right? Like text, could be images, could be videos, customer testimonials, any information that you're trying to build a search on top of. You're going to take all of that data, you're going to run them through machine learning models, and then you're going to generate embeddings. And then you're going to use a CLI or SDK to ingest those vectors into an S3 vector index. Now, there's 2 performance best practices that I'd like you to keep in mind here. Even though the vector index has grown to 2 billion vectors per index, if you are able to isolate your vector data by users, by regions, by some sort of business logic, we still recommend that you distribute your vector data across multiple indexes. And this can really help accelerate your ingestion, right? Because you're able to parallelly write across multiple vector indexes at a time. Also, when you query, you're always querying a subset of your vector space, and so this can potentially improve your query latency as well as lower your query costs. The second thing to keep in mind is that you have the ability to either send several hundred vectors in a single batch to S3 vectors, or you have the ability to send 1 vector at a time or micro batches and send up to 1,000 transactions per second in order to accelerate that ingestion process. So you've done those things, you've got those vectors inserted, and now you're ready, right, for the search strings to come in. So here we have a user sending the search text. That search text will also need to be sent through the embedding model. This is the same embedding model that you use for your source data, and then you want to generate an embedding from that. Then you use that search embedding or the search query embedding, send that to S3 vectors, and there you have it. S3 vectors sends you back the top k nearest neighbors, as well as optionally filters and metadata if you chose that. It really is as straightforward as it looks on this slide. OK, we're going to change gears a little bit and talk about S3 vectors pricing for a few minutes. S3 vectors kind of changes the cost model for vector storage costs. There's 3 really simple pay-per-use components here. First one is pay-per-put. You're only paying for the writes or the uploads when you're doing them. You're not paying for them otherwise. Second, storage. You're paying a fraction of the cost for storage because you're taking advantage of S3's industry-leading cost effectiveness. And then third, you're only paying for queries when you run those queries. You don't have compute spun up. You're not managing compute infrastructure. You're not managing idle capacity. You're only paying for queries when you run those queries. And additionally, you take advantage of a lower query tier if you're managing bigger indexes. We're going to walk through this particular example to see what the math looks like. Here we're building out a RAG workflow. And in this particular example, let's say you have 10 million vectors. Each of them have 1,024 dimensions. So that roughly comes up to about 4 KB per vector. Now we're going to slap on 2 KB of metadata to these vectors, 1 KB of filterable, as well as 1 KB of non-filterable. So roughly, we're getting at 6 kilobytes of vector information. We're going to distribute these 10 million vectors across 40 indexes. So each of the index, let's say, has 250,000 vectors. Now, as our applications changes, as our data changes, we're going to want to keep these vector indexes updated. So let's assume that we're going to roughly upload or rewrite 25% of each of those indexes every month. And then finally, just assuming here that we're running 1 million queries per month across all of these indexes. Let's see what the cost looks like. First of all, the storage cost. So we talked about roughly 6 kilobytes or so per vector with the metadata. That's roughly about 59 GB of total vector storage. And at 6 cents per GB, that's $3.5 for storage costs. Put cost, there's two components here. First of all, you're getting the upfront cost of writing all of these vectors the first time into S3 vectors, right? That's about 11.8 USD with the 20 cents rate per GB. And then remember, we talked about refreshing that vector index, 25% of each index per month. So that roughly comes up to $2.95 recurring per month. 1 million queries, so let's see what that amounts to. There's, first of all, the request charge for the 1 million queries, that's $2.50. There's a tier 1 query, so for the first 100,000 vectors, you're paying the tier 1 rate, which is $1.9. And then you take advantage of the lower tier for the remaining 150,000 vectors, and that's, for the 1 million queries, that's roughly $1.5. So let's bring that all together, right? We're looking at a total upfront cost of $11.8. And then the recurring cost of storage, the writes, like the overrides, as well as the queries, that comes up to $12.4. Even if I put all of that together, that still costs less than your lunch, I bet. All right. For the next few slides, we're going to talk about the integrations that we've had since public preview. There's 2 integrations that I want to talk about. S3 Vectors integrates with Bedrock knowledge bases for you to put an S3 Vector bucket as a backing vector store. And you can create Bedrock knowledge bases directly using Bedrock or using SageMaker Unified Studio. S3 Vectors also integrates with Amazon OpenSearch, and this is if you're looking for lower latencies as well as to build powerful hybrid search applications. Here's what that first integration looks like. So whenever you're starting from source data, whatever your source data is, processing them through machine learning models, generating embeddings, ingesting them into a vector store, like there's a lot of things, there are a lot of variables to consider. And Amazon Bedrock Knowledge Bases is your fully end-to-end managed workflow for doing that. And now you have the ability to choose S3 Vectors as the backing vector store behind Bedrock Knowledge Bases. Here's the second integration that we talked about. There's 2 things here. S3 Vectors integrates with managed OpenSearch as well as with OpenSearch serverless. The first pattern, we tend to see that one for cost reduction, right? So if those of you in the room that have used managed OpenSearch, you'll see the cost of compute can really add up. And here's why you have an option to use S3 Vectors as the backing vector store to do the similarity search while still using the managed OpenSearch hybrid search capabilities. The second pattern we see is for better performance in like lower latencies as well as for hybrid search is you come in and ingest all your vectors into S3 vector buckets, indexes. You have the ability to export those vectors into OpenSearch serverless collections. And then you get the cost benefits of using S3 vectors. And then you can still use the OpenSearch APIs to do hybrid search or anything else that you prefer from OpenSearch. We've got really good customer engagement since public preview for the Bedrock knowledge base integration as well as the OpenSearch integrations. With that, I think I covered all the things that I wanted to talk about on S3 Vectors. I'd love to bring Frank Ouyang on stage to talk about how March Networks is using S3 Vectors to build AI smart search.
Thank you, Bajeta. Hello, everyone. My name is Frank Ouyang. I'm a VP of R&D at March Networks. And Thank you for joining us. March Networks is a leader in intelligent video surveillance solutions. What sets us apart in the industry is our ability to provide business intelligence to a wide range of teams across an organization, from security, IT, to compliance and marketing. Thanks to our advanced AI analytics, we transform video footage into actionable insights that help teams to make smarter decisions faster. Our vision is simple, which is to lead the future of intelligent video solutions. And with AWS as a key partner, we are making that vision a reality. Today, I'm here to share a recent collaboration between March Networks and AWS in building video AI smart search. I hope you'll walk away by the end some practical insights that you can apply to your own projects. For decades, video surveillance has primarily focused on recording events, not interpreting them. Security teams often spend hours reviewing footage, trying to find meaningful moments. Generative AI has changed the game. It's transforming what video systems can do. They're no longer passive watchers, but intelligent partners that help organizations operate smarter, safer, and more efficiently. There's no need to spend hours to scroll through footage. With generative AI, you can simply ask questions such as, show me open, blocked exit doors, and receive results in seconds. Vector database is a key element of that magic. The challenge is to make the system cost-effective and scalable. A lot of our customers produce thousands of hours of videos in 1 hour. That's millions of vectors. And often they want to search up to 2 years of footage. The number of vectors becomes billions. Let's use one use case, blocked exit door detection, to appreciate the challenge and the impact. It is a safety compliance requirement for retailers to ensure blocked exit doors are not blocked. The fine can be hefty for violations. We have a customer paid a few $1 million last year. So instead of reactively paying fines, retailers wanted to actively looking for blocked access to identify hotspots so they can do targeted training and improve operational procedures. For retail, with hundreds of locations, checking in person is not possible. There are cameras pointing to exit doors, but produce thousands of hours of video. To identify blocked exit doors through watching videos is searching a needle in a haystack. AI Smart Search, powered by S3 vectors, can do semantic search to a massive video content, allow retailers to identify blocked exit doors across hundreds of locations with a single query, show me blocked exit doors, turning passive video surveillance into active compliance tool so they can build a more compliant and safer operations. We worked very closely with AWS. This partnership actually significantly accelerated our time to market for AI Smart Search. Video snapshots from all cameras are streamed to S3 bucket. The total number of cameras a customer has can be quite big. We have a bank customer has over 50,000 cameras. In 1 single hour, those cameras will produce 50,000 hours of videos. If a movie is 2 hours, that's 25,000 movies, more than what Netflix has. So, and remember, this is just 1 hour, and cameras run 24/7. So the data volume is huge. So once snapshots are in S3 bucket, Bedrock, Titan, embedding model start generating vectors. And those vectors are stored in S3 vectors and indexed for fast retrieval. Meanwhile, users can start asking questions in natural language. Question got converted to vector by Bedrock as well, and our search service will compare it against the stored snapshot vectors and returns the best matches. Combining MarchDataWorks' deep expertise in video surveillance with the power and flexibility of AWS's AI and cloud platform, this analytical pipeline allows tens of thousands of users run queries again on millions of snapshots and return results in seconds. Based on our experience, S3 vectors offer some key advantages. First, it is cost-effective. It stores billions of vectors at a very low cost, making our system economically viable at a massive scale. Second is the AWS integration. It is seamlessly integrated with S3 storage and Bedrock. This allows our team to focus on building AI features instead of managing infrastructure. And the third one is the Amazon performance and stability well known. That includes S3 massive scale, 11 nines durability, and high throughput, enables sub-second semantic search across an entire video archive. It is essential to note that the technology is advancing rapidly. We are still at early stage. At this point, human verification is key because the results are not always perfect. However, accuracy is improving and new features are rolled out at an incredible speed. The foundation we built today is going to enable far more sophisticated and impactful applications in the near future. With that in mind, let's see the technology in action.
Running a business is hard enough. Finding operational issues and opportunities shouldn't be, especially when potential fines, theft, and liability can't wait. Hundreds of cameras, thousands of video snapshots, now made easy with one simple search. Introducing AI Smart Search, the industry's first generative AI-based voice-activated image search tool.
Show me unattended cash on the desk.
With one easy voice prompt.
Find long queue lines.
Audit your operations to find exactly what you're looking for. Then review the snapshots to find and fix issues fast. Without needing to be on site, you can instantly verify.
Show me empty donut shelves.
Marketing signage changes. Customer service opportunities. Slip and fall hazards, if shelves are stocked. And ensure that safety and security protocols are followed. Search for specific operational and safety issues by uploading an image. Filter your results by location, date, and time. Increase search sensitivity to find exactly what you're looking for.
Show me a blurry image.
And monitor your system for faulty devices. Get instant insights into your operations.
Show me wet floors.
Find opportunities to improve and eliminate potential risks to your business.
Show me open back doors.
Find what matters faster. With AI Smart Search by March Networks.
Thank you for your attention. Now you want Mark back to wrap up.
Very much. Frank, I'd like to thank you, and I'd like to thank March Networks for your great partnership in the preview phase here. The work that you did really helped us build a better product. So, bringing it all together. I mentioned earlier about the problem. We defined what we solved one. We now can ask very interesting questions and get answers from that, but we created another. Our answer to that problem is to bring S3 economics to the problem of cost and complexity, a managed service with S3 economics attached. We understand the meaning of what we are storing. Other things understand the meaning. We can trade these meanings. with the videos, Frank was mentioning that you have customers generating Netflix-like levels of data. That's just going to continue. We're at the start here. There's more. More means more. And with S3 vectors, one of our solutions, but our solution right here, is cloud scale, durable, and it's cost optimized for vector indexes. Also, massive scale. I have up there a number which I just calculated with a calculator one night. It is 2 billion vectors in 10,000 indexes in 10,000 buckets. That is 200 quadrillion vectors per AWS account. Quadrillion. And I look forward to one of you being the first person to come up saying, could I have an increase in my quota, please? Because I've hit 200 quadrillion. Now, we have a session tomorrow. Everything we've discussed, all our integration, it is at the MGM. Raise your phones if you want to go. We turn around, we have this workshop. You get to sit down, bring your laptop. You'll be surprised at how many people don't. I think we had someone complete it on their phone, though, which was fascinating. Probably more fascinating for them. But this goes through all the integrations from start to finish. You'll build chatbots. You'll integrate with OpenSearch. You'll run queries. All amazing stuff. If you do not show up tomorrow, it's published. Written by myself and my colleagues. This is available. Take it home. Share it to your friends. It makes a great Christmas gift, right? So if you're bored over the holidays, gather the kids round. Have them do an S3 Vectors workshop. They'll have something to tell you about in your old age that they resent. So yeah, that's available out there, published right now. You can use that and do it. Also, if you'd like, if you talk to your Amazon solutions architect, whoever's working on the account, they can set up an event for you if a bunch of you would like to do it in a room together. But it's available for you to do alone. Also, again, written by myself and my colleagues, we got 2 blog posts, which we did at launch, Bedrock with S3 Vectors integration and OpenSearch with S3 Vectors integration. We put some work into this. We have a new set of blog posts coming, so we've done our first wave of integrations. People ask us, will there be more? Of course there will be more. But it's like these things take time to cook. But when they're available, you'll know about it. And with that, I would like to thank you for your time and your attention, and enjoy the rest of reInvent. If you have any questions, we will be outside in the corridor. Thank you very much.